Zoom people, can you hear me? Zoom, wonderful, thank you. Hi, everybody. Welcome to in-person Chem 3276. Hope you guys are having a great day so far. I'm Dr. Gray, standing right now. Here I am. This is, yeah. Some of y'all have been to lab. Some of y'all are to go to lab later today. I spoke with Sumera, the morning IA, and I wanted to pass on a couple of things. For those of y'all who are in the 8 a.m. section, in the event that you're like, man, I really hate having hiccups in the lab. Sorry, it's just going to happen with the morning section. And I apologize for that. But I saw some Instagram that said you're not supposed to apologize for things. Instead, you're supposed to thank people for their patience. So rather than saying I'm sorry for that, I should say thank y'all for your patience. But I also kind of think that if you don't apologize for things, you might be a narcissist and a sociopath. So I want to avoid those things. But with that said, our experiment today has basically 3 different parts to it. One of which is the data set that I gave y'all, the Excel spreadsheet. And I had a conversation with one of your classmates today about that data set. And what that data set shows you is you might have a graph that looks a little bit like this. And whenever you plot that data, let me zoom in a little bit, but not too much. On your y-axis, you're going to see something like absorbance 595. You might also be looking at this and thinking, wow, those are really sharp lines with a Sharpie. First time I've ever used these Sharpies. In about 2 minutes, they're going to be blunted on the end and they're going to be a waste. I think there's a light here. There, that's better-ish. Okay, and then on your x-axis, it's going to be protein concentration. In addition to those, so these are the, yes, he is. You have your absorbance values and your protein concentrations, which correspond to this. When you plot that data, you might get something that looks like that. And if you remember last week, we talked about how you really want a linear range. Now, you also have an unknown value. That unknown value, if you put it on that line based on your absorbance value, it might end up somewhere like here. And if you couldn't tell, that's a red dot. That kind of falls, well, where does it fall? And how do you interpret your data? Because if you remember, I said you want a linear range. And you could look at this data set and say, well, that's a pretty darn linear range. But I could also see an argument for this being a linear range. So what do we do? Now, this is where I want you guys to be kind of critically analyzing your data. I want you to look at it and say, well, that red dot, that unknown data point, that falls within this linear range. How would you evaluate that data set? Well, one way that you could do it is by plotting this and getting the R squared value for only that data set. Does that make sense? This one, I'm going to label it A, and this data set is B. Is everyone good with those labels? So you might say, well, you know, whenever I look at value, or if I look at values for my A linear range, well, I get an R squared value of, let's go really dramatic, and let's say 0.676. Oh boy, that's not particularly good, is it? Compared to B, where maybe you have an R squared value of 0.997. Your goal whenever you're looking at an R squared value is you want to see how linear your data is. And so you want something as close to 1 as possible. So if the rise is 1, the run is 1 as well. So that's what you're really looking for. And so whenever you plot this data, and when you look at that unknown, this is where I want you to be critical and, you know, to get ahead of this a little bit. There's not really a right or wrong answer. Does that make sense? There's instead, you've collected this data. You haven't actually collected this data. I gave you this data. But in a hypothetical situation, you've collected this data. Now, I personally look at this and my thought would be, well, I want an R squared value as close to 1 as possible. And I've got a range that shows me an R squared value as very, very close to 1. So that makes me feel good. What's the downside to that data set? Exactly. My unknown falls outside of that range. So what I would write in my interpretation of this is I would allude to that. I would say, well, this R squared value, this data set B is fantastic. It is very linear. Unfortunately, my unknown falls outside of that range. So that would be my kind of, think about this as your rough draft data that you've collected. Does that make sense? So my rough draft data says, well, I've got a linear range with an absorbance from 0.4 to 0.8 and a concentration of this to this. The way that I would follow up on that is I would say, okay, how far can I reduce my concentration? So how many more data points can I collect from here to here and still keep it in a linear range that's pretty close to that? So what I would want to do as a follow-up is I would say, I would want to collect, you know, 4 more data points that basically run from here to here. Does that make sense? That's a great question. That's a hypothetical, totally a hypothetical. So when you're writing your summary paragraph, you know, do something like this. Look at your entire data set and say, well, my data set seems to fall into basically 2 linear paths, or 2 linear, or my curve has basically 2 linear portions. Portion A, portion B. My unknown falls, and this is not looking at this data exactly, but my unknown falls within B. Therefore, I've calculated my unknown's concentration to be this. I feel comfortable and confident with this data. And if I were to like move forward with this, there's not really anything else I would have to do. Does that make sense? How does everyone feel about this graphing portion? Has anyone done the graphing portion already? Okay. Okay. So for those of you all who have not done it, remember that's going to be due as a part of your experiment on Sunday at 11 p.m. Sunday the 26th.
Wait, so no, it's the one that you actually had prior to lab or our actual lab?
Both of them are due. This is all a part of the experiment that you're going to do. Okay, so that's kind of our part 0. Does anyone have any questions about that?
You just have to make the graph, right?
And interpret the results Okay. Any other questions? If something comes up when you're doing this later on this week and you have questions, please feel free to email me and we can set up a Zoom. Deal? Okay. Now, moving on to part 1 of your experiment today. The entire, let's see. Okay, so the intent of part 1 is to look at the Bradford reagent and how the amount of light that it absorbs at a wavelength of 595 nanometers changes over time. Because we really actually don't want it to change over time. The reason being is if it changes, well then what does that tell us about our ability to interpret our results from that? That says that, well, it's dependent on protein concentration, which is what we're using it for, but it's also dependent on time. So if you sorry about that. So what we're doing is 3 different things. We're looking at the Bradford reagent, and we're looking at that, the amount of light that it absorbs over 0, 5, and 10 minutes. No, 0, 2, 5, and 10 minutes. Now, one thing that you need to be sure of is these are time points, not intervals. So you're going to get an absorbance at 0 minutes. You're going to get an absorbance at 2 minutes. You're going to get an absorbance at 5 minutes, and then at 10 minutes. Does anyone want to answer, for those of you who are not in the morning section, how long should this take? 10 minutes. I say that because there are some folks who will interpret this and they'll say, okay, I gotta wait 2 minutes. Measure my absorbance. Now I gotta wait 5 minutes. Measure my absorbance. How much time have they spent? 7 minutes. Do not be the person who spends, well, 7 minutes and then an additional 10 minutes, total of 17 minutes. Do not be the person. You do not need to do that. So we have the Bradford reagent. Then we have one variable that we're introducing, the Bradford reagent plus DH2O. And then we have a second variable, the Bradford reagent, DH2O, and protein. So what we would expect is basically an absorbance of 0 across the board for just the Bradford reagent. Whenever you blank the spectrophotometer, then you measure at wavelength of 595 nanometers, you would not expect this to change because you're not doing anything to change that solution. Now, with the addition of water, again, you don't expect water to change your solution. So you would kind of expect that absorbance to change absolutely nothing. Yes?
So, but that's looking for, I think on the table it says not DH2O, but like the stock. And then the third one is with stock and water.
Okay, sorry about that. So thank you very much. So that would just be the stock. Sorry about that.
But we still don't expect it to change, correct? You just said we have to mix it 3.
Exactly. So thank you for bringing that up. So what you would expect is whatever amount of protein, and I know that there was some confusion in the morning section. Do we use the stock solution for part 3? What do we use for our protein? Well, our Bradford reagent is going to react with protein in solution. It does not matter what that protein is. So what we would expect and what we would like to see is our initial reading of the Bradford reagent plus our stock being our known protein concentration or a known protein sample. Let's say that this is 0.125. There is light that is absorbed when we shoot a wavelength of 595 nanometers out of it. We would expect from 0 minutes to 2 minutes. It's entirely possible that it will change, but we expect it to be a negligible amount if we have thoroughly pipetted this up enough. So let's say that this would be 133. That is a change of 0.008. That is not a significant amount of a change. And whenever I say a significant amount, what you'll see is a significant difference would be 0.125 jumping to 0.250. That would be an alarming number. Because what's going to happen is you might see this jump to 0.133, 0.128, 0.130. The fact that we started at 0.125 and we end at 0.130 for our absorbance, think about this in terms of a percentage. This would be less than a 5% change in the light that's absorbed at 595 nanometers. The fact that we have an absorbance here is good. We want to see an absorbance here. We want our Bradford reagent to basically indicate, yes, there is protein in that solution. What we also want to know is that the amount of protein over the course of 10 minutes is not increasing. Because are we adding any more protein to that mixture? No, we're not. If our absorbance goes up dramatically, that would imply that either the reaction was not completed or you added more protein to that mixture. Does that make sense?
For some reason, if you have a dramatic change, do we do it again in that, or how do you proceed with that?
If it jumps up, so what I would do in that case is I would record what you've got. And in the event that if it goes up after, I would say worst case scenario, after 2 minutes, it's no longer going to be changing. The reason being is that if you look up a protocol or other protocols for doing a Bradford assay, it's going to say mix thoroughly, incubate for 2 minutes. In the event that it, like, let's say hypothetically you get 0.125, 0.947, 0.542, 0.999. In that case, I would say something's wrong with my cuvette, something's wrong with my spectrophotometer, something's wrong with my Bradford reagent solution. I would check with my adjacent lab groups and say, what's happening with yours? Because in the event that it's a cuvette, easy solution, get a new cuvette. In the event that it's the Bradford reagent, then your neighboring groups are going to be having that issue as well. In the event that it's the spectrophotometer, well, then your neighboring groups are not going to have that as well. So try to deduce what are the variables that I can kind of account for. Does that make sense? Yes. Okay, great. So last but not least is this Bradford reagent plus water and our protein. Now, what's intended here is this protein is going to be the stock. But again, it actually does not matter what protein you use, so long as you have some protein in that mixture and you're not changing that. What you would expect is that if you're putting, like if you say 950 microliters of the Bradford reagent, 50 microliters of the stock, then for this over here, part 3, you do 950 of the Bradford, 25 DH2O, 25 of the stock. Well, then you have put half as much of the stock in here. So you would expect your absorbance to respond accordingly. You would expect it to be close to 0.060, something like that. Likewise, you would expect these numbers to not change very dramatically. Does anyone have any questions about that? Yes.
So are you implying that you should instead use keep it to 50 across both sections? Then so it would be 950 of Bradford and 50 of water.
That's a great question. And I guess for the sake of looking at the numbers and saying, yeah, they're similar, for consistency and confirming that, well, what I would do is I would keep the amount of Bradford constant. I would cut it in half actually, so that I would go from the 50 of the stock to 25, so that then I have like a consistent number. Does that make sense? Do y'all have a question? Oh. What's that? Uh-huh. That's going to happen. So I just put these numbers in as like a hypothetical number. So it's going to be concentration dependent. So if you had like a 100 microgram per microliter stock and you added 50 micrograms of that or 50 microliters of that, it's going to give you, actually, your numbers are going to be 4.0, 4.0, 4.0, 4.0. So arguably that's a good thing. Did y'all's change very much over the time frame? Good, good. Okay. So now is part 3. 2. So you look at that, part 2. That's what I intended to draw. Okay, so part 2 is where you are basically emulating part 0 in the sense that this is the point where you have a protein sample with a known concentration. When you get to lab, there will be a stock with a concentration of 10 micrograms per microliter. Now, I posted a video where I showed basically how to make different cereal solutions, where I took let's say 100 microliters from the stock and added to that 100 microliters of DH2O. So whenever I look at my stock, which I'm going to label A, and my dilution number 1, which I'm labeling as B, what I would like to do is say my stock sample has I'm just going to say an infinite volume. But I have a fixed concentration of 10 micrograms per microliter. Now for my first dilution, what can I say about it? My total volume, 200 microliters. Would everyone agree with that? And it has a concentration that is half of what my stock was. So I have a concentration of 5 micrograms per microliter. Does that make sense? Okay. Now, sample C. From this mixture right here, I'm going to take 100 microliters. So what volume is left over of B? I've taken 100, there's 100 left over. Exactly. So I have 100 microliters for sample C, and I'm going to add to that 100 microliters DH2O, and that gives me a total of 200 microliters of 2.5 micrograms per microliter. Yes?
So the leftover volume, that's what we're using to obtain the absorbency, right? Like, you took 100 from the previous dilution, the other 100, where's that go?
That's what you're going to be using for measuring your absorbance.
Okay.
Exactly.
But in the lab, we're doing 25 now. Right?
I'm happy that you brought that up. The reason is, so I said 25, get 25 microliters of the stock, 25 microliters of the water, take of that 50 microliters, take 25 microliters, add that to 975 of the Bradford reagent. Okay. Now, last week, 2 weeks ago, 3 weeks ago, the very first week where we had lab, when you were using your pipette, did everyone observe that they had some level of error with their pipetters? That is absolutely going to be something that carries over. There's always going to be some level of error with a pipette. As a result, if you get 25 microliters from your stock and you put that into a microcentrifuge tube, and you get 25 microliters of DH2O, put that in that microcentrifuge tube. If each time they're 3% off, you're going to have some error, and that's going to be a compounding error. So then when you try to take 25 microliters out and then subsequently take 25 microliters out again, you're going to run into a problem where you're like, oh, I've taken 25 microliters out of where I thought I had 50 microliters. And now, I mean, you wouldn't adjust to see this, but you might be like, I have my pipette set to 25 microliters. And whenever I remove it from my solution, the pipette tip looks like this. I've got a solution, and then I have this void where there's air. So my recommendation is to end up with a mixture of 975 microliters of the Bradford and 25 microliters of a protein sample. Okay. Now, however you get that 25 microliters, it could be from 100 microliters going into here with 100 microliters of DH2O. Does that make sense for everyone? Okay. So taking 25 and 25, you're going to run into a little bit of an error because of the fact that you have not only the instrument, pipette pen has a little bit of an error to it, but also everyone brings in their own, they introduce their own operator error. Okay, how's everyone feel about this so far? Okay, so for part 2, you're going to be generating your own data. At some point, you will have absorbance values. So if you look at that, stronger than the Hulk. Okay. You'll have your stock or your dilution number 1, dilution 2. And for these, you know your concentration. You're going to collect your absorbance. Protein concentration of, let's say it's 10, 5, 2.5. Your absorbance for this might be 0.895. If this is within the linear range, you would expect your dilution number 1 to be 0.450 or something like that. Dilution number 2, 0.225. Dilution 3, 1.25. You're talking about 0. And you might now be beyond the linear range, in which case you might have 0.060 or something of that nature. So what is likely to happen with these solutions is as your concentration gets lower and lower and lower, your absorbance is going to dramatically get lower and lower and lower, in which case you might end up with a negative number. In which case, how could it be a negative number when you have some protein in there? Well, think about it as you have basically diluted the Bradford reagent in that mixture, because you've added a solution that has basically an immeasurable or a not measurable amount of protein in that mixture. Does that make sense? So in the event that you got negative numbers, that's where that's coming from. Now, in the event that you're looking at that and saying, okay, so I'm going to make a standard curve out of 4 data points, and this is something that you're going to be using for your practical final exam later on. Well, what should I do? If I'm doing serial dilutions that are 1-to-1 mixture, and that's going to give me 5 potential data points, that might not be the best course of action for you. So how would you do that? Or how would you basically address that? Well, then what you could do, or as an alternative, you could take your stock and get 90, let's say 190 microliters of your stock plus 10 microliters of DH2O. Is this sample right here going to have less protein than your stock? Is it going to have a slightly lower concentration? It will. This will have a concentration of approximately 9.5 micrograms per microliter. Does that make sense? Then you could follow up and say, well, let's see 180 microliters plus 20 microliters of DH2O. That's a sample with 9 micrograms per microliter. So serial dilutions are not necessarily the absolute end-all be-all way of getting data points to put together a standard curve. You have free reign to do what you want to do with respect to making your dilutions. You do not have to do serial dilutions. Think about it another way. If, let's say, you have, well, actually, yeah, 0.895. Your absorbance for this 9.5 micrograms per microliter is 0.827. And then for 9 is 0.785. Then you have an unknown with an absorbance that is 0.860. Sorry, let me zoom out a little bit. Just off the cuff, could you say anything about this unknown sample's concentration, protein concentration? Well, we've got a 9 microgram per microliter sample with an absorbance of 0.785. The concentration goes up. 9.5 micrograms per microliter is 0.827. 10 micrograms per microliter is 0.875 or 0.895. 0.860. Can you say anything about that? Well, that absorbance is higher than this, and it's lower than this. So what does that make you think about the concentration of that sample? It's in between 9.5 and 10 micrograms per microliter. Does that make sense? So using stepwise and gradual and deliberate reductions, that's going to be helpful. Okay, does anyone have any questions about that?
So well, it just depends on your absorbance levels for your dilutions. In case there's such a wide range like that, we'll have to do something like this to get it more.
This is something, I want you to go ahead and continue with the prescribed data set that's basically described in the worksheet.
Okay.
But as the semester progresses, this is something I want y'all to practice regularly in preparation for the final. So this would be something like next week when you have a little bit of downtime or something. Say, I'm going to take this stock and I'm going to, use 75% of the stock, 25% of water, and do those sorts of cuts for that sort of deviation. Does anyone have any questions about this?
But the lab today is 10 serial solutions.
Yes,
Okay.
absolutely. Okay. All right. So what I now want to talk to y'all about, does anyone have any questions about this? Okay, then I'm going to go ahead and move on to the enzyme that we are going to be trying to purify is lactate dehydrogenase, or LDH. Now this enzyme, we are going to be purifying it from beef heart. And when we purify it from beef heart, well, our purification scheme is going to be, well, we're going to blend it up in a blender. We're going to separate a soluble fraction from an insoluble fraction. We're going to run that soluble fraction over some columns for separation through column chromatography. And that's what it's going to consist of. We'll get into that more later on. What I want y'all to understand now is what our enzyme is going to be doing. We are going to be using an enzyme, our lactate dehydrogenase. What it's going to do is it's going to take lactate and NAD+, nicotinamide adenine dinucleotide. And what it is going to do, it's going to catalyze the production of pyruvate and NADH. So if you look at this, well, we've got a reaction that's at equilibrium. So this could go in either direction, depending on concentration of our products and concentration of our reactants. The player in all of this that we really care about is that one right there. The reason that we care about this is because that's our way of measuring lactate dehydrogenase, or LDH, activity. Because this absorbs light at 340 nanometers. Now, by having a wavelength that we can measure the generation of a product allows us to use that. Does anyone remember what that is? Give you a hint, Gen Chem 2.
Is it the Beer?
It is, yes, the Lambert-Beer law. Now, Next level. Does anyone remember what any of these variables stand for? That's right. A is absorbance. See, not in this case. Concentration. L, that's right. Concentration. L is path length, which I would say 99 times out of 100 is just going to be 1 centimeter. And E or epsilon is, if you did this in organic, it would be your molar absorptivity constant. But as biochemists, we call it the extinction coefficient. Now, absorbance. This is one that always trips people up because they see absorbance and they think light and they think, the units for absorbance are nanometers. That's incorrect. Absorbance, if it has any units, they are simply AU absorbance units. But truly, absorbance does not have any units. This is just kind of a placeholder. So don't stress about that. Concentration, path length, and extinction coefficient. Now, for those of y'all who are algebra whizzes, you might think, oh, well, if absorbance units, there are no units there. Absorbance has no units. Yes. Well, what that means is we have to have all of these units basically produce a product that has no units. Does that make sense? So we have centimeters. Extinction coefficient has kind of unique units in that they are inverse molar, inverse centimeters. Well, if extinction coefficient is inverse molarity, inverse centimeters, path length is centimeters, what's concentration? Molarity, exactly. So effectively, this gives us a means to relate our absorbance to the concentration of one molecule. And the molecule that we are relating it to is this guy right here, NADH, nicotinamide adenine dinucleotide. We're talking about the reduced form of that. Now, this is a very important part of observing lactate dehydrogenase activity. Now, you might look at this, and for those of y'all who are currently in metabolism, you'll say, oh, NADH, I remember that, because we've already talked about glyceraldehyde 3-phosphate dehydrogenase. Oh, that produces NADH. Going through glycolysis, you produce NADH. Going through the citric acid cycle, you produce NADH. There's a number of different metabolic processes that produce NADH. How do we know that whenever we take this B part tissue, how do we know that we're actually observing lactate dehydrogenase activity? Well, I would say that we're kind of at like a 99 to 97% confidence level that we are observing lactate dehydrogenase activity. Why? Because we've stacked the deck in our favor. Because we're going to have such a high concentration of lactate in our reaction mixtures that the NADH that we're producing, well, it's in turn making pyruvate as well. Does that make sense? So we're basically putting so much of our two reactants for lactate dehydrogenase in this mixture that the NADH that we generate, we can confidently say, oh, well, that is a result of these two things being present. Is that good? Okay. Now, one of the ways that you can think about that is we're not directly measuring the presence of lactate dehydrogenase. And that's sort of an abstract question or thought, but we're putting the reactants for lactate dehydrogenase in so that we can then see whether or not one of our products is generated. Now, with all of that said, I mentioned that this was a reversible reaction. how do we know that just as soon as we make our product, they don't revert back? Well, one of the ways that we know that is you have kinetic parameters. You have Km and Emax. Km, does anyone remember what Km is? Going to be your concentration of a reactant that gets you to half of the maximum velocity. So if we stay, basically, if we're not producing enough NADH to reach that Km or go above that, we can confidently say that, well, the NADH and pyruvate are not immediately turned back into lactate and NAD+. Does that make sense? So what we'll be looking for is we'll be looking for an increase in absorbance at 300, or an absorbance of light at 340 nanometers. If that number increases, what does that tell us? Well, that tells us we've generated more NADH. This can be done in a reversible way. We could have this cell extract and pump a bunch of pyruvate NADH in there. And what would we see? We'd see our NADH absorbance deplete, which tells us that we are producing lactate and NAD+. Why are we doing it? Why are we electing to do it this reaction left to right rather than right to left? Money. NADH is much more expensive than NAD+. So we're watching the production of, and so what we're monitoring is our absorbance at 340 nanometers go up. So what we'll be doing this upcoming week is we'll be doing our first catalytic assays where you're going to be given an enzyme extract. You're going to be using your CAPS buffer. So CAPS plus an NAD+ solution plus a lactate solution and enzyme fraction. And you're going to mix all this up. And you're going to observe, well, delta A 340. Now that change in absorbance at 340 nanometers, if you, let's say we have a 0 time point and a 60-second time point, where you have observed your absorbance go from 0.001 to 0.126. You have a rate there. You have a delta A340 over 1 minute. Your absorbance at 340 nanometers has changed from 0.001 to 0.126. I would look at that and I would say, well, I've generated some NADH. This is fantastic. I'm going to take it to the NADH store and become an NADH millionaire. But that is not exactly what we want. What we really want is we want to define units of enzyme activity. Okay, so this number is useful, but we need to be able to interpret that. How can we interpret that number? With the Lambert-Beer law, with Beer's law. We can take this delta A340, and that gets us 0.125 divided by 1 minute. Now, if we have an absorbance, we can set that equal to 0.125 equal to ELC. Would everyone agree with that? Okay. Now this extinction coefficient, this E value, that's something that we have to know. And that is a number that is unique for any and every molecule. For NADH, our extinction coefficient is 6220 inverse centimeters, inverse meters. Our path length, in this case and in most other cases, is 1 centimeter. So when we plug this in, 0.125 divided by 6220 equals our concentration measured in molarity. Sorry about that. Now, that's in molarity. So molarity is what per liter? Moles, exactly, moles per liter. What we need to do is we ultimately, and actually, heck, you could take this a step further and say it's moles per liter per minute. Just as you could say it's molarity per minute, because that was our observed change over 60 seconds. Does that make sense? So what we need to do, though, is we need to know what is the convention, or what's the commonly accepted units of measurement of lactate dehydrogenase. And that would actually be 1 micromole per minute. That is equal to 1 unit of LDH activity. So what we need to do, and I'll scan all these in and post them up on our Canvas page. We need to take this value, this change right here, and get it into micromole per minute. Okay. So the reason that I highlight this is because almost any and every enzyme is going to have a different defined unit of activity. For instance, if you think about a restriction endonuclease. A restriction endonuclease takes a piece of DNA and cuts it. Measuring that in terms of micromoles per minute is a little bit different. And so you have standards that you're going to apply a restriction endonuclease's activity to that you would be different from lactate dehydrogenase. So how would we get basically molarity into micromole? So we have moles per liter, and we just want to get rid of that volume factor. So how would we do that? Well, our total reaction volume is going to be 1 milliliter, which is going to be the same as 0.001 liters. So this value right here, as soon as you multiply that by 0.001 liters, you're going to then have moles, because you've gotten rid of that volume variable, and now you've converted it into moles per minute. Does that make sense? Does anyone have any questions about that? For this reaction, yes, so our total reaction volume is 1 milliliter. That's a great question. Okay. So then the next step is, well, how do we get it into micromoles per minute? Well, all that you have to do is harken back to Gen Chem 1 and say, in 1 mole, I always like to do it, there are 1,000 millimole. And in 1 millimole, there are 1,000 micromoles. And that's what you have to do. Does that make sense? I didn't do this calculation because I don't have a calculator. And I don't see one here. That's the education. So I don't know that how often, well, the elementary education and calculations and stuff. So I was ill prepared for that. But does anyone have any questions about this? Well, that's what you're going to be doing next week, where you're ultimately going to be figuring out what are the units of activity that you observe in a number of different samples. Mixing these two components, incubating for different time points, and seeing what your enzyme activity is. Because what we're using that so that then whenever we begin purifying our protein, we can say, well, have we purified lactate dehydrogenase? Let's check with our catalytic assay. Yes, I see some activity there. Fantastic. Deal? Okay, if there are no questions, well then, I'm gonna go ahead and say, go ahead and take your quiz. If you would like a paper-based copy of the quiz, raise your hand, I'll bring it around. If you need scratch paper, I've got that. But I'm gonna turn the lights on. Lights are coming on now. Oh, my belly, blank screen. Paper-based copy? All right. Whenever you're done with your quiz, have a good one.